not going to be talking so much about how like group theoretic properties of groups are reflected in the topology of the boundary. I'm just going to be talking about what the topology of boundaries of hyperbolic groups can be like. So yeah, I'm talking about really the most simple sort of question you could ask about boundaries of hyperbolic groups. This question here, which as far as I can tell, was originally asked by Capovician and Kleiner, which is just which topological spaces are Gromov boundaries of hyperbolic groups. So here are two spaces that we happen to know are boundaries of hyperbolic groups, a two-sphere and this Manga Cube here, otherwise sometimes called a Manga sponge or Manga curve or something. So here are two spaces, the one on the left quite simple, the one on the right quite complicated. And these are two of the spaces that can be boundaries of hyperbolic groups. And then the question is which other spaces might be. And I suppose there are two directions in which you could push to try to get somewhere with this question. Either you could try to exhibit more spaces that are boundaries of hyperbolic groups to show that lots of spaces can be, or you might try to prove things about boundaries to show that, in fact, not too many things can be. So you might try to prove restrictions on the sort of topology that the boundaries of hyperbolic groups can have. The theorem I'm going to be talking about in the later part of the talk today is in the latter direction, so it's a sort of restriction on the topology of boundaries. But first, I'm going to talk a lot about interesting examples of interesting spaces that can be boundaries of hyperbolic groups. Before I do that, I am going to go through the basic definitions and things first, just to make sure we're all on the same page. Of course, I did that last week as well. So if you are in the intersection of the audience of this week and last week, then that might be a bit boring. So sorry, but I do think I need to just go through the basic definitions to make sure we're all okay with that. So I'm going to say what a hyperbolic group is and what a Gromov boundary is first. Oh, and I should say, giving these talks on Zoom can be a bit weird. It sort of feels like you're just sort of talking into the void, and maybe some people out there are listening. So please do interrupt with any questions if you have any. I think it'll be more fun if you do. Yeah, just shout out. I can't see you, so there's no point raising your hand or anything. I suppose any questions about what I've said so far? Not that I've said very much. Probably not. Okay, I'll get on. Okay, so what is a hyperbolic group? First of all, I need to say what a hyperbolic metric space is, and this is a sort of metric definition that tries to capture something about the geometry of the classical hyperbolic spaces that we've all seen, like the hyperbolic plane. We say that a geodesic metric space is hyperbolic. Well, I suppose I should say a geodesic metric space is a space where any pair of points can be connected by what we call a geodesic. So that's a minimal length path, so that the length of the path is equal to the distance between its endpoints. So a geodesic space is hyperbolic if there exists delta, so that all triangles in the space are delta slim. So a triangle is just three vertices connected by geodesics, so these minimal length paths. That's all I mean by triangle in the metric space. And we say it's delta slim if we get a picture like this one I've drawn here, where each of the three edges of the triangle is contained within a delta neighborhood of the union of the other two edges. So I've drawn this just for one of the edges here. So we see that the bottom edge is contained within distance delta of the union of the left edge and the right edge. So I've drawn these sort of banana-shaped neighborhoods that have radius delta around each of the other two edges, and we see that these bananas just about cover the bottom edge of the triangle. So this triangle is just about delta slim. So that's a delta slim triangle. And then we say that a group is hyperbolic if it acts geometrically on a hyperbolic geodesic metric space. So we're studying the group by its action on a metric space. And we sort of link the geometry of the group to the geometry of the space. I suppose I should say that what does it mean for an action to be geometric? I don't want to get into too much detail about that, but just briefly, it means that the group's acting by isometries, so it's respecting the geometry of the space. It's acting co-compactly, So the quotient by the group action is compact. That sort of means that the group sees everywhere in the space. There aren't like big regions that the group never visits. And finally, the action is properly discontinuous, which means that any compact subset of the metric space is moved off itself by all but finitely many of the elements of the group. So that's saying that generally elements of the group do move things around quite a lot. So we say that the group is hyperbolic if it acts geometrically on a hyperbolic geodesic metric space. And then it turns out that, in fact, any geodesic metric space on which the group acts geometrically is hyperbolic. So when you have it for one space, you have it for all of the spaces that the group acts nicely on. So that's a hyperbolic group. Easy examples. So first of all, some examples of hyperbolic spaces. So bounded metric spaces are always hyperbolic just because you can take delta to be the diameter of the space, and then trivially any triangle is delta slim. Trees, including the real line, which is sort of a tree, are all hyperbolic with delta equals 0. If you try drawing a triangle in a tree, you see that each edge of the triangle is in fact covered by the union of the other two, so you don't even need to take a neighborhood. And finally, the motivating example, Hn, the n-dimensional hyperbolic space. So here we have delta is, you can show it log of 1 plus root 2, I think. So those are some hyperbolic spaces. Following on from that, we get some examples of hyperbolic groups. So finite groups act geometrically on bounded metric spaces. So finite groups are hyperbolic, but that's not very interesting. Free groups, they act geometrically on trees. So free groups are hyperbolic because trees are hyperbolic, and as a sort of special case, Z is a free group with one generator. Z acts geometrically on R, so Z is hyperbolic. And then the first really interesting examples are fundamental groups of closed hyperbolic manifolds. So if M is a closed hyperbolic manifold, then pi1 of M is hyperbolic because it acts geometrically on Hn. I didn't put my other example. Also, in a sense, random groups are hyperbolic. So if you write down a random complicated presentation for a group, then with probability approaching 1 as the length of the presentation tends to infinity, the group is likely to be hyperbolic. So that's just my brief introduction to hyperbolic groups. Sorry if you saw it last week. Any questions about that? Otherwise, I'll say something about boundaries. Nope, I'm going to move on to say something about boundaries now. So first, what is a Gromov boundary? For a hyperbolic metric space X, we first of all define the boundary of a hyperbolic space. So the Gromov boundary defined from a base point x0 is the set of geodesic rays gamma that map into X, with gamma of 0 is the base point x0. So geodesic rays, these are like rays, so maps from 0 to infinity to the space, so that for any finite subset of that interval, then the length of the restriction of gamma to the interval is equal to the distance between the images of the endpoints of the interval under gamma. So gamma is gamma is a geodesic ray, which means an isometric embedding of this interval 0 to infinity into X. So the boundary of X is this set of geodesic rays quotiented out by an equivalence relation, where we say that two geodesic rays are equivalent if they remain just a bounded distance apart from each other forever. So we can imagine a geodesic ray as being like a direction you could look in starting from x0, and then the boundary is the space of directions. Of course, we can see in my notation on the left, I've just written boundary X. I haven't written boundary x0 X or something. So I'm omitting the base point, and that's because the base point doesn't really matter. Choosing two different base points leads to topologically the same space as the boundary. So that's the boundary of a hyperbolic metric space. Now, if a group G acts geometrically on a hyperbolic space X, then we just let the boundary of G be the boundary of X. And this might seem like cheating, but it's actually fine, because given any two spaces X and Y, say, on which G acts geometrically, so say they're both hyperbolic, then in fact the boundary of x is homeomorphic to the boundary of y. So it makes sense to make this definition. This doesn't actually, it looks like it depends on our choice of x, but it doesn't really. So that's the boundary of a group. Some basic properties just to sort of start things off on narrowing down what boundaries can look like. First of all, the boundary of a group, a finitely generated group, is always compact. This is basically a consequence of the Arzelà-Ascoli theorem. There's sort of only a compact set of directions you can look in within a finitely generated group. Secondly, it's metrizable. So it's naturally a topological space. In fact, it's a topological space that you can equip with a metric, if you like, which I suppose isn't true for all metric spaces, but is true for, sorry, isn't true for all topological spaces, but is true for all of the topological spaces I like thinking about. And finally, it has finite topological dimension. So I don't want to go into too much detail here, but for a topological space, you can define dimension in, well, a lot of different ways. Here, I suppose I'm referring to the covering dimension. And what I'm saying is that for any boundary of a finitely generated, any boundary of a hyperbolic group, that space has finite covering dimension, and similarly finite lots of other sorts of dimension if you like to define dimension differently. So those are just some easy or easy-ish restrictions that say that the boundary of a hyperbolic group can't be too bad. It's at least got these nice properties. Okay, so those are our first properties of hyperbolic groups. Now let's see some easy examples of hyperbolic groups. First of all, the boundary of any finite group is empty. That's just, obviously that's boring. So a finite group acts geometrically on a finite set, on a bounded set, and there aren't any geodesic rays in a bounded set. So the boundary is empty. There's nothing in it. So that's not very interesting. Next easiest example, the boundary of Z is, well, Z acts geometrically on the real line. So the boundary of Z is the same as the boundary of the real line, which is 2 points, plus infinity and minus infinity. The boundary of, now here things get interesting. The boundary of a free group on at least 2 generators is, well, it's the boundary of a tree. So for example, the boundary of F2, the free group on 2 generators, is the boundary of an infinite tree where every vertex has degree 4. And as a fun exercise, you can try to convince yourself that the boundary of any such tree is a Cantor set. So, right, we're already seeing quite exciting topological spaces appearing here, and this is still quite easy examples. I think the Cantor set is I suppose as mathematicians we're all sort of used to it, but I think it's the sort of space that people are surprised by when you introduce it for the first time. So it's nice to see it arising quite naturally in geometric group theory here. Finally, a very nice space that can be the boundary of a hyperbolic group, just a nice, very simple space, is the spheres can be boundaries of hyperbolic groups. So if M is a closed hyperbolic N manifold, then pi1 of M acts geometrically by deck transformations on n-dimensional hyperbolic space. And, well, just like you can draw the Poincare disk model of the hyperbolic plane, whose boundary is then a circle that goes around the edge of the Poincare disk, the boundary of n-dimensional hyperbolic space is Sn-1. So the boundary of our group, pi1 of M, is also Sn-1. And I sort of think of that as an exceptional case. Normally, boundaries of hyperbolic groups are sort of complicated fractal-like things, but it so happens that for these manifold groups, they can be much nicer. The boundary can actually be a sphere. In fact, this is the only way in which the boundary can be a manifold. The boundary isn't itself a manifold unless it's a sphere. Yeah, and no manifolds other than spheres arise as boundaries of hyperbolic groups. Okay, so I think those are my easy examples, and basically, so far, I've just been repeating things I said last week. So as I say, if you were here last week, sorry. Any questions before I'm about to move on to some slightly less easy examples of spaces that can be boundaries of hyperbolic groups? Okay, right, on to our harder examples. The first of them is the Sipinsky Carpet. So this is a complicated fractal-like space. Well, it is a fractal. And I haven't included a picture, but you can get it by starting off with a square, say a 1 by 1 square, and then you remove the middle 1/3 by 1/3 square. And so you're left with sort of 8 squares around the edge. And then you remove the middle 1/3, well, now 1/9 by 1/9 from each of those 8. And then you repeat that process forever, sort of drilling more and more holes in your square forever. And in the limit, you get the Sipinsky carpet, which can be a boundary of a hyperbolic group. And I'm going to explain in a second, I quite like this construction. So I'm going to explain in a second how the Sipinsky carpet can be realized as the boundary of a hyperbolic group. Next example, the Manga Cube. So that was on my first slide. This is the theorem of Bernoulli, says that the Manga Cube is the boundary of a hyperbolic group. And then Champetier proved that this is the generic case. So I said something brief earlier about random groups being hyperbolic. In fact, random groups are hyperbolic with Manga Cube boundaries. So this is sort of generic. Almost all hyperbolic groups have the Manga Cube as their boundary in a sense. There are actually higher dimensional analogues of the Manga Cube called Manga Compactor. And it's a theorem that in the two-dimensional Manga... before I say that, maybe this is slightly confusing. The Manga Cube looks like a 3-dimensional space, or at least close to 3. In fact, the Manga Cube is only a 1-dimensional topological space. Its covering dimension is only 1. So sometimes I'll refer to it as a 1-dimensional space, and that surprises people sometimes, but it is. And then it has higher dimensional analogues called the Manga Compactor in dimensions greater than 1. And it's a theorem of Zrenishnikov that the 2-dimensional Manga Compactum is the boundary of a hyperbolic group. And then it's also a theorem of Dumara and Osida that the 3-dimensional version is the boundary of a hyperbolic group. Of course, there are analogues of Manga Compactor in dimensions greater than 3, and it's actually an open question whether or not those are boundaries of hyperbolic groups. The 2- and 3-dimensional cases come from Coxeter groups, and I think it can be shown that the higher dimensional ones can't come from Coxeter groups. So if we're going to realize those as higher dimensional, if we're going to realize higher dimensional Manga Compactor as boundaries of hyperbolic groups, then there needs to be a new idea. So that seems quite difficult.
Quick question.
Yeah.
So when you say the Manga Cube, is that really just one homeomorphism type, or are there different? You know, are you saying that generically a Gromov hyperbolic group has one homeomorphism type of boundary?
I am, yeah, right. So
okay, wow.
Yes, they almost all have up to homeomorphism the same boundary. You can then start asking questions about richer structure, like metric structure, and it turns out that I think they don't all have to have equivalent metrics. But yeah, up to homeomorphism, they really do all have almost the same boundary. Sorry, they really do almost all have the same boundary. Yeah.
Okay.
And then there are these Pontryagin surfaces. This is the theorem of Zrenishnikov, that these are boundaries of hyperbolic groups. These are quite weird spaces. As an example of one of these, imagine a Sipinsky carpet. So this has a lot of sort of square boundaries of bits that you've cut out, because so you get a Sipinsky carpet by repeatedly cutting out squares from your square. Now, on each of those squares, glue the opposite edges together, sort of like you do for a torus, and you'll get a very complicated 2-dimensional topological space called a Pontryagin surface. And then there are similar constructions. There are infinitely many. This is an infinite family of things, but you can do sort of similar stuff to get the other ones, I think. And it's a theorem of Zrenishnikov that these are boundaries of hyperbolic groups. So I suppose the point I'm trying to make is boundaries of hyperbolic groups can be really quite crazy, complicated fractal type objects. And then another nice construction by David. That says David and Januszkiewicz. That's quite a faux pas. It's actually Davis and Januszkiewicz. Sorry, I've mistyped that. So replace David there with Davis. So this is saying that there are these complicated high-dimensional spaces, which are homology spheres, by which I mean that they sort of, from a homological point of view, they look like manifolds, even though they're not actually manifolds. And also from a homological point of view, they actually look specifically like spheres. So these are sort of things that you can't really distinguish from spheres using homology. So they're quite weird spaces from a topological point of view. And some of these, it turns out, can be boundaries of hyperbolic groups in dimension, I think at least 5 or 6. So those are some examples. I'm just trying to give a flavor here. On the next slide, I'm going to talk a bit more about the Sipinsky carpet. So I'm going to prove this lemma, which says that if M is a compact hyperbolic 3-manifold with non-empty, totally geodesic boundary, then the Gromov boundary of the group is a Sipinsky carpet. So M, maybe it's a bit confusing if I'm using boundary in 2 different senses here. So when I say M has a boundary, this is a compact manifold, so I mean boundary in the standard sort of way that manifolds can have boundaries. Then I'm talking about a group having a boundary, and that's a Gromov boundary. So yeah, okay, those are slightly different things, I suppose. So lemma says that we can get the Sipinsky carpet from the fundamental group of a compact hyperbolic 3-manifold with non-empty, totally geodesic boundary. Okay, so let's prove this. Okay, so first of all, since the boundary of the group is the boundary of a space on which it acts geometrically, and the group acts geometrically on the universal cover of M, which I'm denoting M tilde, we just try to describe M tilde and then hopefully see that the Gromov boundary of M tilde is a Sipinsky carpet. So that's our strategy. First of all, let's try doubling M along its boundary. So this is manifold boundary, not Gromov boundary. So let's let M primed be the union of 2 copies of M. So we take 2 M's together and then glue them together by identifying their boundaries. And then M primed is a closed hyperbolic 3-manifold. The fact that it's a hyperbolic manifold sort of follows from the fact that the boundary of M was totally geodesic. So M primed is a closed hyperbolic 3-manifold. So the universal cover of M primed is H3, 3-dimensional hyperbolic space. Okay, and therefore the universal cover of M is actually a subspace of H3, bounded by infinitely many isometrically embedded copies of the universal cover of the boundary of M. And the boundary of M is, again, totally geodesic, so it's a sort of 2-dimensional hyperbolic thing. So the boundary of M has universal cover H², the hyperbolic plane. So the universal cover of M, of this manifold we started with, is a subspace of H3 bounded by infinitely many isometrically embedded copies of the hyperbolic plane. There's going to be a picture on the next slide. But first, I'll finish off the proof. And then if we think about this, what I've just described, what that means for the boundary, it means that the boundary of M is the boundary of H cubed, so as S is the 2-sphere, minus the bits sort of cut out by all of these isometrically embedded copies of H². So minus a dense union of open disks with disjoint closures. So each of the copies of H squared, the limit set of that in the boundary of H cubed is going to be a circle, and then the Gromov boundary of the universal cover of M is the complement of the interiors of all of these circles in S². And then it's a theorem from classical point set topology that whenever you start off with a 2-sphere and remove a dense union of open disks with disjoint closures, you end up with a Sipinsky carpet. So what we have must be a Sipinsky carpet. And that's all a bit difficult to imagine. So here's a picture I've tried to draw. It's also quite difficult to draw, so I don't know how much this picture helps. But what I've tried to draw here is H3 in the upper half space model. So H3 is everything with z coordinate positive, so it's bounded by the xy plane. Now, all of these isometrically embedded copies of h squared all look like hemispheres that are orthogonal to the xy plane. So the universal cover of M is everything that sits outside all of these hemispheres I've drawn. Then its Gromov boundary is everything that's in the xy plane plus the point at infinity minus the interiors of all of these shaded circles, which are the bits sort of cut off by these isometrically embedded copies of h squared. So, of course, I've only drawn finitely many of the h squareds here. They are in fact dense in the plane. So, I mean, I've tried to give a bit of a flavour of that by drawing some of them very small and very close to some of the other ones. But you're going to have to use your imagination a bit to picture what would happen if I'd drawn all infinitely many of these isometrically embedded copies of h squared. So I think this construction, maybe it's a bit difficult to imagine, but any questions about anything I've said so far? Any comments or thoughts or anything like that? They don't need to be questions. I'm very happy with comments.
Is it easy to see that the group in question is actually hyperbolic?
Oh,
I mean,
well,
it's not acting as, yeah.
Yeah, right. So it's easy-ish to see that. Yeah, so the group acts geometrically on this universal cover of M, just because M is compact, so the action is co-compact, and always actions by deck transformations are properly discontinuous. So what we'd need to convince ourselves was that the universal cover of M was a hyperbolic metric space. And this follows sort of by the picture I've drawn, because M is actually a convex subset of H3, and hyperbolicity is passed on to convex subsets.
Right. Yeah, makes sense. Thanks.
So yeah, the geometric picture sort of yeah, right. So we sort of inherit hyperbolicity from H3 itself. Thanks.
Could you say a word about why the union of disks is dense?
Why it's dense? Yeah, I guess right. Okay. So if it weren't, then there would be some point in the boundary that some point in the boundary that is separated from all of these disks, all of these isometrically embedded copies of h squared. And then if you imagine getting closer and closer to that point, you must be getting further and further away from all of those copies of h squared. But M, the manifold we started with, is compact. So nothing is, so every point in M is a bounded distance from the boundary of M. So that property lifts to the universal cover as well. So that can't happen.
I see. Thanks.
Sure. So yeah, it comes from the fact that M was a compact manifold. Yeah, thanks for that. Any other questions at all, or I'll move on?
Yeah, I had a question. Can those hyperplanes intersect at infinity?
Right. So yeah. So no, I need them not to intersect at infinity, because this disjoint closures thing. We need these open disks that I'm removing to have disjoint closures to be able to apply this this theorem that lets us deduce that it's a Sipinsky carpet. And happily, that is actually the case. So if they did meet at infinity, so if they met at the boundary, then you'd get these two. I don't know if you can see me, but I'm using my hands to sort of gesture a sort of bit where two of these hyperbolic planes, which are lifts of the boundary, are sort of coming towards each other asymptotically. So they're getting closer and closer and closer asymptotically towards each other. And if that happened in the universal cover, then that would actually have to happen in M as well. And that doesn't happen in M because M's compact. So the boundary never sort of asymptotically curves in on itself as it would have to. So yeah, that can't actually happen. So through your questions, hopefully I've justified now all of the conditions that I needed to apply this classical topology theorem about Sipinsky carpets. And does that clear that up, or anything else?
Yeah, now why can't they? I mean, couldn't you have two geodesics sharing the same point at infinity?
Yeah, you can do, but for that to happen, so they've got those two geodesics do get infinitely close as you go off towards infinity, and then imagine just pushing those two geodesics down to M rather than the universal cover of M, and you'll still get these two geodesics in different sort of bits of the boundary getting converging on each other, which can't happen in the boundary of a compact thing. So there just isn't really sort of room for that downstairs.
Okay, I see. Thank you.
Thanks for the question. I'm about to move on. Yeah, good. Okay, now I'm going to start talking about local connectedness. So local connectedness is a nice sort of topological property that, I don't know, spaces that aren't locally connected can be a bit scary. So it'd be quite nice if we knew that boundaries of hyperbolic groups were locally connected. And that's sort of what this theorem of Bestvina and Mess gives us. So the theorem says that if the boundary of a group is connected and does not contain a cut point, then the boundary is actually locally connected. So a cut point is a point where if you remove that point, then the boundary becomes disconnected. So like a sphere doesn't have any cut points, but a line does have lots of cut points. So the theorem says that if the boundary is connected and doesn't contain a cut point, then it's actually locally connected. So that's nice. That sort of tells us that the boundary of a group can't be too horrible. Well, I suppose there's this no cut point condition, which we might not really like, but happily then Bowditch and Swarup came along and proved that, in fact, if the boundary is connected, then it doesn't contain a cut point. So putting these two together, we can sort of delete half of the conditions of the Bestvina and Mess theorem. So this tells us that whenever the boundary of a group is connected, it's actually locally connected. And I talked a bit last week about connectedness of boundaries. So the condition that the boundary be connected doesn't really matter that much in practice, because if it's not connected, then you can sort of decompose the group in along some of its finite subgroups to get pieces where the boundaries are connected. So basically the boundary is always going to be at least built out of these locally connected things. So that's quite powerful. Immediately it gives us a theorem of Capovician and Kleiner that basically classifies, at least almost classifies, the one-dimensional Gromov boundaries of groups. So the theorem of Capovician and Kleiner says that if the boundary is one-dimensional, connected, and doesn't contain a local cut point, so I'm now saying local cut point rather than just cut point, then there are only three possibilities. It's either a circle, a Sipinsky carpet, or a Manga Cube. So a local cut point is just a point where if you remove that point, then you locally disconnect the space. And that's something else that I talked a lot about last week. So local cut points sort of tell you about other sorts of decompositions of the group. So again, this is sort of telling you that if the boundary is one-dimensional, then you can decompose the group into pieces whose boundaries are all either circle, Sipinsky carpet, or Manga Cube. Then maybe describing the boundary of the group in terms of the boundaries of those pieces probably isn't so simple, but still, I mean, this gets you some of the way towards a classification of one-dimensional boundaries of hyperbolic groups. And that just really follows from this Bestvina and Mess theorem. So it uses some sort of topological theorems that say that if a topological space is locally connected and has all these other properties that Capovician and Kleiner show that boundaries of hyperbolic groups have, and it's one-dimensional, then there are only these three possibilities. So this theorem of Bestvina and Mess is quite limiting on the topology that at least one-dimensional boundaries of hyperbolic groups can have. So sort of motivated by that, I did some work, finished last year, on a sort of slightly higher dimensional analog of that. So the result of this theorem, the point is to replace connected by simply connected and locally connected by locally simply connected. So this theorem says that if G is a hyperbolic group with a connected boundary, then the boundary is locally simply connected if and only if the complement of any point in the boundary is simply connected. So that's like saying that the boundary doesn't contain a cut point, but sort of a dimension higher, where connected gets replaced by simply connected. So that's the statement of the theorem. Of course, in the locally connected case, from the previous slide, we were able to delete the cut point bit of the conditions by this theorem of Bowditch and Swarup, which sadly we don't get to do here. As far I don't know whether it's true that it'd be nice if whenever the boundary was simply connected, the complement of any point was simply connected. That would be the analog of this no-cut point theorem of Bowditch and Swarup. But I think, as far as I can tell, that's an open question. So I'm going to state some questions. So first of all, first question. So here I've replaced connected with simply connected. There are sort of high dimensional analogues of this as well, where like simply connected is about filling loops. Also, you might wonder about filling spheres, filling 3 spheres, filling 4 spheres, and so on. So the obvious question is, would this theorem remain true for high dimensional analogues of these conditions? I don't know. For a long time, I thought I could answer the question, but I couldn't, sadly. And second question, this is what I started saying before. So suppose that the boundary is simply connected. Does it follow that the complement of any point is simply connected? So this seems natural to ask because it's true in the lower dimensional analog of the theorem, and it would let us simplify the statement of the theorem that I've stated on this slide, but I have no idea if it's true. So that's the statement of this theorem. Actually, I thought I was going to go a bit slower than this, so it looks like I've got plenty of time to finish this off. I'm going to say something quite brief about some of the proof of the theorem, but I'm not going to go into too much detail. I suppose before I do that, any questions about the statement? Is that clear, hopefully?
Is there an easy example of a group whose boundary is not, whose boundary is locally connected, but not locally simply connected?
Locally connected, but not locally simply connected. So there definitely are examples. Yeah, okay. So I don't know how easy an example this qualifies as, but okay, we had that construction of the Sipinsky carpet earlier.
Okay, yeah, right, okay. So
that doesn't work because that's not simply connected. Oh, sorry, but that is locally simply connected.
Sorry. No, that's not locally. Wait, is that locally simply connected? That looks not locally simply.
No, it's not. Sorry, it's not locally simply connected. Yes.
Okay, good. So that it is locally connected. So okay.
And it is locally connected.
Okay, good. Thank you.
So I think I've confused myself, but hopefully that answered the question. Did that answer the question?
Yes.
I think so.
Okay,
Thanks.
and here in the theorem, I see. So it's not locally simply connected, and it also is not the case that when you remove a point, it's simply connected. Okay, cool.
Yeah, right. So yeah, it's sort of very not simply connected. It's got loads of holes. Yeah, so happily it's not a counterexample to my theorem. And yeah, okay, thanks. So I think so the question, just to get this straight in my mind, you asked for an example of a boundary that was locally connected, but not locally simply connected. And yes, okay, if that was the question, yeah, Sipinsky carpet is the answer. Great.
Great, thank you. Yeah.
Thanks. Okay, so I'll say something not too complicated about a bit of the proof. The proof uses a simplicial complex you can associate to the group called the Rips complex. The Rips complex is a simplicial complex, well, for a given constant d. Its vertex set is actually just the group, and given a finite subset of the group, we say that they span a simplex if and only if the diameter of that subset is at most d with respect to the word metric. So this is a bit like the Cayley graph, really. If the constant d was 1 and we just looked at the one skeleton of the complex, then you immediately get the Cayley graph. But in general, this is a simplicial complex that you can build for any group, and it's a nice space for the group to act on. And it's particularly good when G is hyperbolic, in which case this simplicial complex is actually contractible as long as the constant d was big enough. So this is a nice way of building a nice contractible space for which on which the group acts. And now let's let K subscript n be the subcomplex of K spanned by just those elements whose distance from the identity element is n. So this is like a sort of sphere in the Rips complex. So you can imagine these as a sequence of progressively larger spheres in the Rips complex going outwards towards the boundary. And then the whole point of the proof really is to try to approximate the boundary by these simplicial complexes. Using these, you can get continuous maps that sort of project inwards from the boundary onto Kn. So that's the sort of setup. And then it's a step in the proof is to show that as well as mapping inwards from the boundary onto Kn, you can actually also map outwards from at least the 2 skeleton of Kn onto Kn plus 1. So you can sort of map things, you can define maps In that map the 2 skeleton of Kn onto the 2 skeleton of Kn plus 1. So from the radius n bit to the radius n plus 1 bit with a couple of properties. First of all, In doesn't move vertices very far. There's a uniform bound on how far In moves anything. And secondly, In is simplicial, as a simplicial map after uniformly boundedly many barycentric subdivisions of Kn. So this is a bit technical, but really it's just saying that there's a sort of bound on the complexity of these maps. So once you have these maps, you can compose loads of them together. So you could do In, then In plus 1, then In plus 2, all the way up to Im. And if you take that limit of these maps as m goes to infinity, this converges to a continuous map mapping Kn onto the boundary of G. So we had these projections inwards from the boundary of G onto Kn. Now that should say the 2 skeleton of Kn. So it turns out then that you can go sort of in the opposite direction a bit. You can map outwards from the 2 skeleton of Kn onto the boundary of the group under the conditions that I've set. And this is sort of an approximate inverse to the map Pn. So it helps us if we want to study the boundary using these spheres in the Rips complex. So that's the setup. And then all I've got left is just this picture, which then sort of shows the strategy of the proof. So I've here got some spheres Kn and Kn plus 1. And then at the far right of the screen, I've got the boundary of the group. I've drawn a sort of complicated squiggly loop in black in the boundary. And to show that it's locally simply connected, we probably want to fill that loop or something. So what we do is we use Pn to map down to Kn. And then we fill the loop there and map back out to the boundary. And okay, it's only approximately an inverse. So we get a red loop that maybe looks a bit like our original black loop, but probably isn't quite the same. You could do the same thing, but now using Pn plus 1 to map onto Kn plus 1 and then mapping back. And maybe this is slightly more accurate. This mimics the original loop slightly better. It approximates it a little better than the original one. Keep doing these and take a sort of limit, and you eventually end up being able to fill the loop you started with, which was your goal. That's actually everything I was planning to say. Obviously, I'm 5 minutes short, which is a bit unusual. But so I'm happy to take any more questions or comments or thoughts or anything like that. I hope I wasn't rushing too much.
Can you say something about why the Rips complex approximates the boundary? I didn't quite understand that.
Right, yeah, sort of. I suppose what I've tried to say is a bit vague. So, I mean, I'm not quite. So, what should I say? So, So, how can I justify the idea that these spheres in the Rips complex? So these are like bigger and bigger spheres in the Rips complex. So they're sort of larger and larger. Okay, so I guess one thing you might think is, okay, so the boundary of the group is the space of all directions that that you could look in, starting at the identity element of the group. And a direction is sort of partially determined, only partially determined, but sort of partially determined by what direction it is up to radius n. So you're looking in a direction, which element of the group distance n from the identity are you looking at? And there are sort of only finitely many of those. And as you go out further and further outwards, these radius n things give you sort of more and more information about the directions that you could look in. And so they look, the space of like directions up to radius n looks more and more like the space of directions all the way out to the boundary. And then, so sort of the sphere in the group of radius n sort of approximates the boundary as you let n tend to infinity. And then these subcomplexes of the Rips complex just give that a nice bit of topological structure that it turns out helps you approximate it in a stronger way. Sorry, that was extremely vague. I don't quite know what to say. Sorry.
Well, thank you. So, but the dimension, you're getting bigger and bigger simplices, right? As you
yeah, that's true. Yeah, that's a good point. Yeah. So the simplices in the Rips complex are much higher dimension than the boundary is probably. Yeah, actually, definitely. Yeah. So the boundary is a much lower dimensional space than these simplices in the boundary. But if we can sort of imagine the sizes of the simplices as going to 0 as we let the spheres go, the radius of the spheres go to infinity. Otherwise, the spheres are just becoming too big. So, okay, imagine we're rescaling the nth sphere so that they're all about the same size. We're rescaling metrics on those. Then you have all these big simplices, but they tend to end up not really mattering because, well, they're getting smaller and smaller and smaller. So I suppose then the large scale topology of these large spheres looks like the boundary. Another thing I could say, actually, to make this actually rigorous, is that the boundary of the group is actually the projective limit of all of these spheres in the Rips complex. So that's quite a precise way in which we can say that the boundary is approximated by these spheres.
So they're kind of being flattened or something. Is I mean, you're picturing.
Yeah, I guess they're sort of being flattened out. I mean, their depth is at most the constant d that we were using to start off to build the Rips complex, which isn't growing as n goes to infinity. So that depth sort of matters less and less as we let the spheres get bigger.
Okay, thank you.
Sorry, I'm aware that I'm not really saying anything particularly rigorous there.
Yeah, no, I'm sure. But is that why the Rips complex was constructed, or to understand the boundary, or is it? It seems like it comes up in a lot of places.
Not really. So the Rips complex, yeah, right. So I think at least my understanding is that the first place in which the Rips complex comes up, at least for hyperbolic groups, is because it's contractible for D large enough. And if you're studying sort of finiteness properties of groups, like, I don't know, do they have type Fn or Fpn or Fln or all of these finiteness properties that I don't really understand, then what you need to do is construct actions of your group on contractible spaces, ideally finite dimensional contractible spaces, and the Rips complex is a perfect thing to use to do that.
Uh-huh. And when it's hyperbolic, you're saying that it's approximating that kind of object is the sphere at infinity or something like that?
Well, I'm not saying that the Rips complex approximates the sphere at infinity, just that large spheres in the Rips complex approximate the boundary at infinity. So I'm taking bigger and bigger spheres, and just those subspaces, I'm saying, approximate the boundary.
I see. Thank you. I enjoyed your talk.
Oh, thanks. Thank you.
I have a question that's more general, and I'm not quite sure if it makes sense, but is there a way to talk about the boundary of a group when you were thinking about, say, hyperbolic orbifolds, or does that not really make sense in this context?
So, like a hyperbolic orbifold group, I don't know much about orbifolds, but they have universal covers in the same way that manifolds do, don't they? So I guess that if you have a hyperbolic orbifold, shouldn't its universal cover be HN still? In which case you'll still get a sphere, I think. Is that right? Does that make sense? So I'm saying, is it true that if you have a closed, I don't even know if closed is the right word for orbifolds, but if you have a closed hyperbolic orbifold, is it the case that its universal cover is HN? If so, then its orbifold fundamental group is has boundary the n-1 sphere still.
Okay.
So
thank you.
If you're right, I don't know anything about orbifolds.
Yeah, I don't know a ton about orbifolds either, but I was curious.
Sure.
Well, isn't it still acting properly discontinuously? So it seemed like that's all you wanted for the hyperbolic.
Yeah, I guess that's my thought. Yeah, so you didn't need the group to act freely on the space or anything. You just needed proper discontinuity. So yeah, it should still be okay, I think.
Okay, that makes sense. By the way, as someone who attended last week, the intro was still very helpful.
Oh, good. Yeah, I mean, yeah, I suppose I should never really expect people to. I mean, I forget the vast majority of talks I'm in, so good.
Does it matter which constant d that you take in the Rips complex?
It just needs to be big enough.
Just big enough so that it's
small,
contractible.
nothing really works.
Okay.
Well, actually, I think when I was proving the theorem, I needed it to be a bit bigger than just that. But
okay.
I could write down, if I spent enough time looking at it, I think if d is at least 1,000 delta plus 1,000, that would be plenty. So you can definitely describe how big d needs to be in terms of delta.
Okay. Then what's the map PN like? I had a hard time imagining what's the map PN? You said there isn't. Yeah.
Yeah. Okay. Let me see if I can remember how to construct this. So. Yeah. Okay. So this is quite a useful sort of trick, I suppose. First of all, consider the group elements that make up the vertices of Kn. So these are just the elements of the group that are distance n from the identity. And it turns out that by taking like a sort of shadow of each of those in the boundary, you get an open subset. You get lots of open subsets of the boundary that cover the boundary. So you can form a cover of the boundary by sets associated to the vertices of Kn, and so that these sets are sort of shadows of group elements. Then take a what's the word, a partition of unity subordinate to this universal cover. Another way of thinking of that partition of unity is as a map from the boundary to r to the power of the set of vertices. So it assigns, so the map assigns to any point in the boundary a real number to each of the vertices of Kn, so that those numbers add up to 1. That's just another way of saying what a partition of unity is. And then that's almost the same as a continuous map from the boundary to the simplicial complex. So partitions of unity and maps to simplicial complexes are sort of quite close to the same thing. I guess you can do that whenever you have a partition of unity, that's the same as a continuous map from the space to the nerve of the associated simplicial complex. And Kn turns out to be the nerve of a covering of the boundary. And so you can do that.
Okay, I see. Yeah, thanks.
So, okay, can you say then again how this all works? So I think so that map makes sense. The other one in the other direction that's only from the 2 skeleton, right? And I assume that's something like you take 3 vertices of a triangle, associate them with 3 points in the boundary, and then use the local the simply connectivity to kind of fill that in or something, right?
Yeah, right. And that's very close. Yeah, that's pretty much the right sort of idea. Yeah. So the point is you've got a lot of triangles in Kn+1 that you need to fill, which you sort of do by filling them in the boundary, which you're assuming is simply connected. And yeah, that's basically it.
But then what is can you go back to the other picture? What is the,
sure, yeah.
Okay, you take some limit, explain again how the sort of punchline happens.
Okay, I guess the bit I haven't justified is that you can fill loops in Kn and Kn+1 and so on, but you sort of can. So
okay,
the strategy then is start off with a loop in the boundary, project it down to Kn, fill the loop there, and project the filling back out to the boundary.
Okay.
And then you've got a filling of a loop that is quite close to your original loop. And then by doing a bit of analysis, you can sort of control things so that
I see.
taking the thing as n tends to infinity, you get a filling of your original loop. So for the local simple connectedness, you also need to sort of control the size of the filling because, well, that's the whole point, really. You want local simple connectedness, but it turns out you can do that as well.
Okay, so you're using the global simple connectedness to fill the loops in Kn.
Yeah.
And then somehow you can control the size of that process as you push out towards the boundary all the way. Okay. Is that
right? So you sort of need to know that you can fill loops in Kn. You need to know you can fill loops in Kn in a sort of bounded complexity sort of way, so that it's not getting more and more complicated as you go outwards. And you can apply a sort of compactness argument to do that, and that turns out to be where this requirement that not just the boundary be simply connected, but the boundary minus any point be simply connected as well comes in. So that bit is a bit technical, and I know I didn't really explain that at any point. So I should say this proof is quite similar in some ways to the Bestvina and Mess proof. Right? You can sort of trace through in the proof of my theorem here. You can see the Bestvina and Mess theorem, proof of that theorem. All of those components are still there in the simple connectedness case, but then you need to do a bit more work to make some other things work. So that part you can have a look at for from Bestvina and Mess as well to see to see that.
Okay, thanks.
Just one more question. Do we know which groups satisfy the assumption that are the boundary that are locally simply connected?
Not really. That would be nice if we could somehow associate some group theoretic property to all of this, but I don't know. That might be a bit ambitious. I don't know of anything that could tell us anything in that direction at all.
Okay, that's all right. Thanks.
Thanks. Well, thank you for all the questions.
Okay, so if there are no further questions, let's thank Ben again. Yeah.
Thank you.
Thanks. Thank you all for coming.